This video discusses the differentiability within an interval. First of all, you have to know what we mean by differentiability. We talked about the differentiability at a given point during our last video. You have to know it very well to understand the materials discussed in this video. If you need help understanding the differentiability at a given point, how to check the differentiability of a function at a given point, there's a separate video. I'll have the link posted down below in the description. Once you know how to check the differentiability at a given point, then we can look at the differentiability over an interval. Let's say we have a function y equals f of x. Let's assume that this function is differentiable not only at one point, but within an interval of values. That interval could be the entire real line from negative infinity to positive infinity, or it could be a portion of the real line, maybe from 0 to infinity, or maybe negative infinity to 0, or maybe something like negative 5 to 100. So likewise, we can always have a function which is differentiable not only at one point, but within an interval. We will look at the graph of a function like that. Always we are going to need the axes, x and y axis. Here's the origin, and I need to label these axes, and I'm going to use capital letters to label those axes. Always make it a habit to label the axes using capital letters. Alright, now I need to draw a function which is differentiable not only at one point, but within an interval. If I draw a function like this, it is differentiable. As seen from this graph, fx should be continuous at least from somewhere here until somewhere here on the x-axis. Let's assume that this graph is the graph of y equals f of x. Last time we had a specific point and we labeled that point as h comma k. That is to check for differentiability at that point. Now I do not need to select one point and label it as h comma k. Instead, I will select some random point within that interval where this graph is differentiable. I'm going to label that point using lowercase x. Just like earlier, I'm going to label this point on this graph as P0. So what are the coordinates at P0? P0 has coordinates. X coordinate is lowercase x, and the y coordinate is of course given by this equation f of x. Therefore, the y coordinate is equal to f of x. Now, just like our last discussion, I'm going to measure a very small positive quantity delta x along the x-axis to go to the right hand side from point P0. Let me assume that the delta x is at a distance like this, and on the graph I'm going to label this point as point P1. The gap right here is equal to delta x. What should be the coordinate point right here? That x coordinate point should be equal to x plus delta x. Therefore, I can write down the coordinates at P1 as x plus delta x, which is our x coordinate, comma, the y coordinate is given by this equation, f of the x coordinate. Then I can write down the y coordinate as f of x plus delta x. Now I can once again consider another point P2 to the left hand side of P0, once again at a distance delta x. Let me assume that this new point is somewhere here. I'm going to label this point as point P2. This gap between the two parallel lines between P0 and P2 is also equal to delta x. Now, how should you write the coordinates at P2? This coordinate right here on the x-axis should be equal to x minus delta x. Therefore, the coordinates at P2 should be equal to x minus delta x, comma, the y coordinate is once again f of the corresponding x coordinate. Therefore, it should be f of x minus delta x. We know, as seen from the graph of the function y equals f of x, that function is differentiable not only at this point p0, but also over an interval along the x-axis. Therefore, we have selected the point p0 technically as any random point. Last time we wrote down two equations for differentiability. One equation for the right hand differentiability by considering the points p0 and p1. We wrote down the slope between those 2 points as delta x approaches to 0 as the right hand differentiability. And the second equation we wrote for the left hand differentiability by considering the slope between p2 and p0, once again as delta x approaches to 0. Now for this case also we can do the same thing. Last time the equations we had were d plus as x equals h and d minus as x equals h. In this setup we don't have any h. Instead, that h has now become x. Therefore, all I have to do is once again to write down these two equations, replacing that h of that equation by lowercase x. Alright, now I'm going to write down the right hand differentiability for this configuration by considering the slope between the points p0 and p1 as delta x approaches to 0. We will write this as the right hand differentiability, which means d plus as x equals lowercase x. I will write this as limit delta x approaches to 0. Of course, there's nothing magical here. We simply need the slope between the points p0 and p1. We just have to look at their corresponding coordinates. We know the slope is given by the difference of y coordinates divided by the difference of x coordinates. So we already know the coordinates at p0 and p1. The difference of y coordinates should be f of x plus delta x minus f of x. So let me write it on the numerator, f of x plus delta x minus f of x. In the denominator, the difference of x coordinates should be x plus delta x minus x. Those two will be simplified to become just delta x in the denominator. So this is our equation for the right hand differentiability. Please note that once you apply this equation and solve for differentiability, your answer will have x unless your function is a first order linear equation. Right here and right here we have x terms. Do we know a value for x? We don't. What we know is the value of delta x. We know that delta x is approaching to 0. Alright, now similarly we will write down an equation for the left differentiability. Left hand differentiability, we write it as d minus at x equals lowercase x. This should be equal to limit delta x approaches to 0. The numerator should be, we look at the points p2 and p0. We know the slope is written as the difference of y coordinates divided by difference of x coordinates. p0 is right here, p2 is right here. The difference of y coordinates should be f of x minus f of x minus delta x. So let me write it down as that, f of x minus f of x minus delta x. And then I need to write down the difference of x coordinates. It should be x minus all of this term, x minus delta x, x minus delta x. Please note that you have to distribute the negative symbol right here into each of these two terms inside that factor. Then the x's will be cancelled and the denominator will be simplified to become a positive delta x term. Therefore, the denominator right here is just delta x. This is the equation we have for the left hand differentiability. Now what you need to pay attention is that this point p0 was just selected as a random point within that interval of differentiability for this function y equals f of x, and that point p0 has an x coordinate labeled as lowercase x. When you apply these equations, we obtain a function of all slopes for the given original function, which means we have the differentiation as a result of this process. D plus at x equals x and d minus at x equals x will always give you a function of x. Do we get two different functions by using these two equations? Absolutely not, because we know that this function is already differentiable. Differentiable means this left-hand differentiability should be equal to the right-hand differentiability for any x value within that interval where the function is differentiable. In fact, that function is called the function of all slopes. Of the original function f of x. When we say the function of all slopes of an original function f of x, it is called the differentiation of that original function f of x. So mathematically speaking, it is called the differentiation of f of x. To find the differentiation of f of x, you can use the right-hand differentiability or the left-hand differentiability as you wish. If you find the differentiation of a given function f of x using either the right-hand differentiability or the left-hand differentiability, then that procedure is called by using the first principles. Differentiation using the first principles. We will do an example, but before working on an example, I need to also show you some other notations other than d plus x and d minus x that are used to say that we are differentiating a given function. Differentiation of a function f of x, of course, can be given by d plus x equals x, and that's going to be equal to d minus x equals x, because the function is differentiable within that entire interval. And because of that equality, we don't need to specify that it is plus or minus. We can simply write it as just d x equals x. And some people simply write it as d subscript lowercase x. There are some other notations also possible. Another notation for the same differentiation is limit delta x approaches to 0. The denominator is delta x, but if you look at the numerator, whether it is the right-hand differentiability or the left-hand differentiability, the numerator has the difference of y coordinates. Here also it is the difference of y coordinates. The difference of y coordinates can be written as delta y. Therefore, another symbol widely used for the differentiation of f of x is limit as delta x approaches to 0. We write it as delta y divided by delta x. However, this statement right here is somewhat long, and instead of using these Greek symbols at these places, we use English letters and write this as dy by dx. When we say dy by dx, it means as limit delta x approaches to 0, delta y over delta x. That exact same thing written in a shorter way. Since y is also equal to f of x, dy by dx can also be written as d by dx f of x. They are all standard symbols widely used for the differentiation of the function f of x. In addition to that, so if your original function is f of x, the differentiation is often written also as f prime x. We know y is equal to f of x. So when you say f prime x, you can also write it as simply y prime. So these are all widely used symbols to say we have differentiated the function f of x. You can use any of these symbols as you wish. Please note that if you found the differentiation of a given function using the right hand differentiability or the left hand differentiability at a common point x equals x, then that process is called the differentiation using the first principles. Now we will look at an example. Here's your example. Differentiate y equals x squared using the first principles. Two quick comments. Comment number 1. We know that the function y equals x squared is differentiable for all reals, because for the entire real line, the graph of y equals x squared is a nice, smooth, continuous function, which means it is a differentiable function. Comment number 2. When we say differentiate using the first principles, you may use the right hand differentiability equation or the left hand differentiability equation. You are not showing the differentiability. Here you just have to differentiate this given function. Within that question itself, it is embedded the fact that the given function is actually differentiable. It is differentiable, therefore you are given the task of differentiation. For the first principles, I can use either the right hand differentiability or the left hand differentiability. Alright, let's see how to answer this problem. Note that for this case, our f of x is x squared. We will also need f of x plus delta x if you are going to use the right hand differentiability, or if you are going to use the left hand differentiability, we will need f of x minus delta x. I personally prefer to use the right hand differentiability. Therefore, I'm going to write down f of x plus delta x. If your f of x is equal to x squared, what should be f of x plus delta x? That should be equal to x plus delta x, everything squared. Now, we will go ahead and find that differentiation. I will use d plus at x. This equation is equal to limit as delta x approaches to 0. On the numerator, we have f of x plus delta x minus f of x, all of that divided by the denominator is just delta x. Now let me go ahead and substitute those values. This is equal to limit delta x approaches to 0. On the numerator, we know that f of x plus delta x is equal to x plus delta x, everything squared. So this first term should be x plus delta x, everything squared. That minus f of x is equal to x squared. In the bottom, we just have to write down the term delta x as it is. Now it is just a familiar limit problem, and we need to evaluate that limit. We cannot go ahead and do the direct substitution of delta x equals 0, because if I do the direct substitution, the numerator is going to be x squared minus x squared, which is equal to 0, and that divided by another 0, which is undefined. Therefore, we need to do some further simplifications. When I do some further simplifications, this is limit delta x approaches to 0. On the numerator, how do you simplify this part, x plus delta x, everything squared? You need to expand that. You can easily expand it if you still remember the college algebra result. If you have to expand a plus b, everything squared, this should be equal to a squared plus 2ab plus b squared. I'm going to use that result and expand that x plus delta x, everything squared. It will be then equal to x squared plus 2 times x times delta x, and there will be another plus delta x squared. And then we have minus x squared minus x squared. In the bottom, I have a delta x term. Now I can simplify the numerator. Here I have x squared, and here I have another minus x squared. Those two will be simplified to become 0. This is equal to limit delta x approaches to 0. On the numerator, I only have these two middle terms, 2x times delta x plus delta x squared. From those two terms, I'm going to factor out a delta x. Then from the first term, I will have a 2x, and from the second term, I will have a delta x. In the bottom, I will just have a delta x term. Now it's time to do the simplifications. We can divide out the delta x and the delta x from the numerator and the denominator respectively. That is because delta x is not equal to 0. Delta x is only approaching 0. Therefore, we are allowed to perform that operation. Now I can do the direct substitution. I can put delta x equals 0 for this only remaining component of that function. Therefore, when I put delta x equals 0, this reduces to be equal to 2x. That means if I differentiate x squared, we get the answer of 2x. Please note that we obtained this answer by simplifying the right-hand differentiability of the function f of x equals x squared. Therefore, this result can be finally written down this way. The differentiation of x squared is equal to 2x. We can write it as d by dx x squared equals 2x. Why did I write a d by dx x squared like that right here? Remember, we had it written as dy by dx. We also said we can write this as d by dx. Since y is equal to f of x, we can write it that way. That f of x right here is equal to x squared for this specific example. That's why I wrote down the final answer this way. Writing down the final answer in a proper way is always expected in this class. Alright, that's an example for this first principles method. If you would like to try another example, show using the first principles that the derivative of sine x is equal to cosine x. I would like to assign this as a homework problem. When you solve this problem using the first principles, you will need this equation at some point. Sine a minus b is equal to sine a cosine b minus cosine a sine b. Alright, I'm going to stop the video at this point. Thank you so much.